A hidden mechanism trips. A bronze jaw snaps open. Metal strikes metal with a sharp ringing clang. The alarm sounds perfectly, signaling disaster, and yet no one in the room has felt even the slightest tremor. The year is AD 132. Inside the Han Dynasty court, a polymath named Zhang Heng is presenting a massive 6-foot bronze urn to a highly skeptical emperor and his officials. Arranged symmetrically around the outside of this urn are 8 bronze dragons, each pointing toward a specific compass direction. Waiting directly below each dragon is a bronze toad with an open mouth. Sometime around AD 143, the machine triggers. The dragon facing west drops its ball, but the ground in the capital is completely still. Zhang Heng's political rivals immediately mock the device as a failure and a parlor trick. Several days pass. Then a breathless messenger arrives from the west. A devastating earthquake has leveled parts of Gansu province roughly 400 miles away. The disaster struck in the exact direction the bronze dragon pointed. In Han cosmology, an earthquake meant the emperor was at risk of losing the mandate of heaven. The mandate of heaven is the belief that a ruler's divine right to govern is contingent on their virtue and can be revoked by the cosmos through natural disasters. By knowing precisely where a distant quake occurred days before human messengers could arrive, the government gained a massive head start to dispatch aid and manage the political fallout. The falling ball provided highly specific directional data. It told the Han military exactly which road to take to dispatch relief forces across an empire spanning thousands of miles. To accomplish this, the device had to sense a tremor hundreds of miles away, isolate the exact direction the wave came from, and mechanically trigger exactly one corresponding alarm, and it had to do all of this using only bronze levers and gravity. Achieving that level of accuracy required a highly sophisticated grasp of physics. Zhang Heng was utilizing the laws of inertia, principles that Western science would not formally identify for another 1500 years. By isolating a physical reaction inside a bronze jar, Zhang Heng successfully extended human perception across hundreds of miles of terrain, completely bypassing the limitations of the human nervous system. The core operating principle driving this machine is inertia. Inertia is the physical tendency of a heavy isolated mass to remain perfectly still, even if the container resting around it is suddenly shifted. This chart shows the waveforms of seismic activity over a long distance. To detect an earthquake 400 miles away, Zhang Heng's device had to solve a resonance problem. The Earth's crust quickly absorbs fast shock waves, leaving only slow, rolling surface waves intact at the 400-mile mark. As a rolling wave passes underneath, the bronze urn shifts slightly, but due to inertia, the suspended heavy mass remains perfectly fixed in position. This requires a mechanism known in the historical texts as the du-zhu. The du-zhu is a central pillar acting as an internal inertial sensor, tasked with converting that tiny relative movement between the stationary mass and the shifting Earth into a triggered alarm. Zhang Heng didn't know about tectonic plates. His genius was flawlessly applying the mathematics of inertia to build an instrument tuned to the exact frequency the Earth was transmitting. Here is where history turns into an unsolved puzzle. The physical blueprints detailing exactly how the du-zhu was built are completely lost. For nearly 2 centuries, modern engineers have been arguing over what was actually inside that urn. The first major hypothesis is Theory 1, the suspended pendulum. This model was heavily championed by early modern seismologists in the 1880s, primarily the British engineer John Milne. In Theory 1, a hanging mass swings right when the urn shifts left, dropping a ball. But seismic waves push and pull. This back-and-forth motion causes the pendulum to oscillate chaotically, triggering multiple levers and dropping several balls at once, ruining the directional data. To solve this, seismologists proposed Theory 2, the inverted pendulum. Instead of hanging from above, a heavy mass is balanced on a narrow vertical pin. When the ground shifts, the mass topples over completely in one direction and physically locks into place, preventing it from bouncing back and triggering a second dragon. The flaw with Theory 2 is stability. An inverted pendulum is incredibly fragile, making it exceptionally difficult to calibrate to the precise long-distance sensitivity described in the Han Dynasty texts without it tipping over from a slamming door. Designing a purely mechanical linkage that guarantees a single unidirectional trigger from a chaotic rolling wave is an engineering feat that modern reconstructors still cannot solve perfectly. Within 500 years of its invention, the original devices and all of their technical manuals vanished. They were likely hoarded, dismantled, or destroyed during periods of violent war and dynastic collapse. The only surviving descriptions we have were written by literary scholars. They left behind beautiful poetic accounts of the exterior artwork and the dragons, but they lacked a mechanical vocabulary to document the mathematics happening inside. It is a harsh reminder that technological progress is not a permanent upward curve. Highly advanced, fully functional systems can be completely erased from human history if the knowledge isn't fiercely protected. Today, the quest to recreate the device continues. A celebrated 2005 replica managed to work by resting a single ball gently on a pedestal, but this design entirely sidestepped the complex 8-ball mechanism described in the ancient texts. In 2025, Chinese researchers launched a new project to rebuild the machine using only 2nd-century metallurgy and woodwork. They realized that previous tests using modern precision machining had actually ruined the reconstructions by ignoring the friction and physical constraints that Zhang Heng had to design around. Even without the blueprints, Zhang Heng's central concept survives. Using an isolated inertial mass to detect relative ground movement is the exact same principle powering modern broadband seismometers and submarine fiber optic cables. Submarine fiber optic cables are telecommunication lines along the ocean floor that can detect physical movement by measuring fluctuations in transmitted light pulses. We may never know exactly how the bronze gears inside a dragon machine fit together, but Zhang Heng's philosophy, the realization that humans can build machines sensitive enough to listen to the planet, remains the undisputed foundation of global earthquake detection today.